potentially have this sheet attached to it, and you might want to understand what the things on the sheet mean so you can apply them in the exam, all right? Just as an example. And this, hopefully you can see it okay, has stuff like properties of logarithms. There's some stuff you probably don't need, but there's some combinatorics. On the back there are some summations, some manipulations, some properties of asymptotic analysis. You probably don't need all these, but some of you might use some of them, and so it's okay. These are in your toolkit if you need them, but I'm just saying, get the cheat sheet, right? It should be beneficial. At least get familiar with it, right? So here's my housekeeping. Okay, let's talk first about Ripple. Ripple 1's done. This week you're moderating. If you haven't done your moderation, do that, please, by Monday, 4 p.m., or you won't get that mark. The only other thing I wanted to mention is that a few people had some trouble with the interface. I'm new to Ripple, so I kind of took this for granted, but when you make a new contribution, you have to click a big button at the bottom that says something like AI assessment or something. Basically, the people who made Ripple, they have an AI stood up behind it, which will look at your question and try and give you feedback. I personally, this is interesting, they're the teaching and learning experts, not me, so if they think that we should have an AI there, that's why we have an AI there. I'm not questioning them about that, but just be aware that you have to click through, you have to let the AI look at your thing and give you feedback before you can actually get through and publish it, okay? Next week, ECA, Wednesday, so there's no class on Wednesday. If you have a Wednesday tute, you've been reallocated, you should check your timetable. Some of them have been moved to, I think, Monday, Tuesday, Thursday, and Friday. So you could be anywhere. Please just be aware of that. I'll talk a little bit quickly about this question on ed. This is a fantastic question. Somebody has posted saying, hey, look, I'm a comsci 505 person. I think I'm doing well. I think I'm keeping up. However, there's all this stuff going on ed that I have absolutely no idea about. That's fair enough. It's a great question. What we want you to do is check in early if things like this come up. So they're saying, look, I don't know what A1 is. I don't know what MOS is. I don't know what Unix is here. And I think it's got to help sessions. Like trying to explain a function that converts everything in your array to be a string that says, this is what you get given. This is array of some index and get the element out, right? You're allowed to do that. C can do that. You can do that too. What we don't want you doing is stuff like saying if thing in list. Because if you say in Python, if thing in list, it looks like a single line. It looks like a single function, returns yes or no. But actually under the hood, Python's going through everything in the list in linear time to find whether or not the thing's in there, right? And so it's hiding a bunch of functionality that you should be implementing yourself. So that's kind of the rule of thumb. Just ask still if you're not sure. But otherwise, hopefully that gives you kind of a temp check. And I put something at the end of the last spec that kind of explains that. Any questions about housekeeping, assignment, etc. before we move on? Yep. Yeah, good question. So the question is, how can Gradescope evaluate my string printout? Because it might be different between students. We don't test that, actually. So another one that people have been getting a bit stuck on is with dynamic list, is it full, right? To me, and we talk about list today, so we'll get to this, if there is any position in that list that could take on an element, it's not full, so return false. Otherwise, return true. However, that's just convenience function for you. We won't be rigorously testing that. However, what we will be doing, the tests kind of look like this to give you an idea. We get dynamic array, x equals dynamic array. We generate 1 million elements. We randomly flip coins, appending, prepending, reversing, blah, blah, blah. We also keep a real list that does the same stuff, and then at the end, we check that the elements are the same in the same order. So things like that is what we're testing, right? So we're trying to see if your data structure is behaving the way we expect it to. That's a great question. Does that help? Yeah. Any others? No, I don't think I see any hands. Wave if you're furiously wave. No? Okay, cool. Let's go. Let's go with the lecture. So today, we're going to have some fun, as always. We're going to talk about, oh, actually, sorry, one more housekeeping item. This one, back to the doc cam. Suppose it's an exam, right? Suppose it's the end of your exam, and I ask you a question like this. Can you see that okay? So it says, specify the big omega for this algorithm, and then there's an algorithm there. Are you going to be annoyed at me about a question like this? Who would be kind of annoyed about this question? I would. Now, my greatest fear as a coordinator is sitting there when the exam goes in and waiting for the phone call. Because when you ask a question, the examiner leaves the room and they ring me and they say, hey, some student said on question 1A there's a mistake. Right? My heart stops. And I say, the student's wrong. But sometimes the student's right. So what's wrong with this question? Yep. Yeah, well, there's a couple of things possibly that are wrong with this question. The first is that here we have a case where we run in constant time, right? Sorry, I was going to write of 1 and then I thought that was a bad idea. So if the list happens to be divisible by 2 with no remainder, that thing returns. Otherwise, it goes through and it sums up the elements in the list, right? And this is linear time, I hope you agree. But the problem is you're going to hit this constant time operation when? In what case? The best case behavior of this algorithm enters this, right? The worst case behavior of this algorithm enters the else and does a linear pass, right? Does the question say anything about which case we're talking about? No, okay? Now, I've told you if we don't say otherwise, assume worst case, but it's a bit sloppy. So the point is, now, how does this come back to you? If you're making a question on Ripple, I want you to be very precise. I want you to think very carefully about what you're saying. This question is underspecified. If the answers were something like, could be this, or maybe it's this, well, this is true if you're talking about worst case. Oh, sorry, you can't see. Oh, wait, I've taken a photo. Hang on, let me figure this out. Go away. I actually have no idea how to work this thing, so I'm going to use the other one, low-tech solution. And let me put the light on. Well, if I take a photo on this one, we're screwed. So it could be this, if we're talking best case, or it could be The other one, if we're talking worst case, but the question doesn't say which case we're talking about, right? So it's a bad question. So please try and specify. Same thing. Can you see this okay? Here's a question. Specify the big O bound for this function, or of this function. 10n cubed plus 3n squared plus log n. Select one of these answers. Which ones are candidates that are correct? What do you think about the function? What's the highest term in the function? Yeah, so is this true? Yeah, is this true? Is this true? Is this true? Which one's the tightest bound? This one, right? So the student probably is asking which one's the tightest bound, but they didn't say so. And again, I've told you to assume that. But what happens is if I write a question like this on exams, I get phone calls, right? So if you're writing questions for your colleagues, please try and be conscious about this. We need to be very precise. And you can see, I even told you last week how I made a mistake last year, not being precise enough about a question I asked. So please just try and think about that a little bit as you're going through doing your Ripple questions. Awesome. All right, let's go to sorting again. Okay. Remember that last week we talked about sorting and we learned some cool sorting algorithms. If you've been to the tutes, you've sort of been through them again. Simple ones, some run slower than others. But what all of these sorting algorithms had in common was that they're comparing keys, right? So for example, I might just change color here. So all of the sorting algorithms we looked at, bloody technology, they do some comparisons, right? So the point is that if we want to say whether element A or B is bigger, we compare them. We say which one's bigger, right? So there's always this comparison going on. Examples we had, bubble sort, insertion sort, selection sort. Do you remember what these ones run in? Worst case? N squared, worst case, right? And then you had merge sort. What's the worst case of merge sort? N log n, merge sort. What about quick sort? N squared, but O of what? N log n what? Expected, right? If we do random pivoting, okay? So we've seen some sorting algorithms, but all of these in common have this idea of comparison, right? So last week I said something like, hey, you can't do better than merge sort. Now, when I'm talking about better here, I'm talking about a comparison model where I'm interested in counting the number of times I have to compare element A and B, okay? And so last week I said something like, hey, merge sort is as good as you can do in terms of the number of comparisons that must be done to sort some input in the worst case, right? Now, I'm going to try and convince you that this is true. And that is that any comparison-based sorting algorithm has to have big omega of n log n comparisons in the worst case. It's lower bound at n log n. You can't do better in the worst case. Of course, you might do better in some other case. Did I show you that? Did we see an algorithm last week that actually could do a pass-through in linear time? It was bubble sort, right? Remember that bubble sort, if the list is already sorted, it compares a pair, a pair, a pair, a pair, and then it's done. And you didn't do anything. That's actually doing a linear number of comparisons. But that's the best case, right? I'm talking about worst case. So you have to do, what I'm claiming here is you have to do at least n log n comparisons in the worst case. So what we're going to try and do now, and I'm going to mess up the math for sure because I am a bit nervous doing math in front of a big cohort and most of you are better at math than me. So we'll give this a try. I'm going to try and mount a case about why you have to do at least n log n comparisons. All right, so what we're going to do is try and find, or we're going to try and derive a worst case lower bound. Now, I'm going to diverge from the slides, and that's what's making what I'm about to do a little bit dangerous for me. But it's all in the slides if you're interested. So, and that's why if you can't see the desk, I've got 6 pieces of paper laid down in front of me because I've been thinking about this all week. All right, so what happens when you compare two elements? What is the output of a comparison? Basically, you can say, is A greater than B? What is the answer? What are the two, I've given it away, what are the two possible answers? True or false, right? So let's build a comparison model. And I'm just going to sketch some notes here. And I think the reason I'm doing it this way is because last year I found people got a bit hung up on this because I skimmed through it a bit fast. So I think if I kind of slow it down and show you from first principles what's going on, maybe you'll understand a bit better. So in a comparison model, we can compare two elements A, B. I'll always use less than, but you can use any comparator you like. And you're going to actually get some tree that's like this. No and yes, right? Do we agree? And so if I have some other stuff going on underneath with other comparisons that I'm just not going to show, what you'll notice is that the left half of this tree, and let me explain what a leaf is an output, okay? So when we're sorting, we can go down, oh, that's kind of hard to see. Can you see it okay? Yeah, okay. What you do is you go down this tree of comparisons until you get to the bottom. And at the bottom, you've got a leaf. And what a leaf is a configuration of the output, okay? So essentially, if I have this tree with a bunch of stuff going on and I get to a leaf, all the leaves on the left side of this tree have something in common with each other. What is it that they have in common? It's in the top there. Yeah, what is it? A has to be what? Is A less than B? No. So A's come where? Before or after B's? After? All this binary comparison is confusing, right? If A is less than B says no, then A has to be greater than B, right? So that means that all the outputs on this side of the tree are blah, 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 B, blah, 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 A. A has to be on the right of B. I hope you agree, right? Now, all the leaves on this side of the tree obviously are the other way. Blah, 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 A and then B. There are lots of different potential ways they could be next to each other, maybe not. Do you buy what I'm selling here? Do you agree that you're going to have some leaves with A on the left and B on the right and the other way? And that decision was made at the root of this tree, but other decisions can be made at other leaves of the tree. Okay, so we've built a comparison model where we agree, at least you're warming up to the idea, that walking through this tree gives us some path to an output, right? Okay, cool. So what I'd like to point out now is that these clouds obviously have a bunch of other comparisons in them, and I think it's a little bit annoying to draw, so I'll put it on the doc cam again, and let's hope I don't take a photo. Oh, I'm on the wrong one. So hopefully you can see that. So here's one I prepared earlier. You've got 3 elements in a list, right? A, B, and C. And if you have A less than B, no on the left, on the right, at the leaves you can see the orderings that come out from sorting these 3 elements, right? Now, you might start thinking about, well, I've got 1, 2, 3, 4, 5, 6 leaves, right? And that's because my input had 3 elements, okay? So we can generalize this a bit further. I'll leave that up there for a sec, but it's going to be captured in the lecture recording if you want to go back. What I'll do then is let's think about permutations of a list. Go back to a different color. So what do we know about permutations of a list? Given a list of n elements, I'll just write given n elements. How many ways are there to arrange those n elements? There are n factorial ways. That's right. We have n factorial permutations. And you do see that in the tree diagram at the bottom here, actually, right? We had 3 elements come in that we want to sort. We had 6 leaves, 3 by 2 by 1 is 6, right? And that generalizes to any n, okay? At least any n greater than 1, I guess. I need to be a bit careful. So if we know that we are interested in sorting a list of n elements, there can be n factorial permutations. That means that the leaves of a tree like this, there have to be how many of them at least? There have to be at least n factorial, right? For any tree, for any n inputs. So must be at least n factorial leaves in our comparison tree. Let's think a little bit about, and look, we can use this tree here as an example. What if we didn't have at least n factorial leaves? What would happen? Could we actually always give the correct sorted output? No, right? The algorithm wouldn't be correct. So we have to have at least n factorial leaves, or the algorithm would be incorrect, right? So hopefully now you agree that if we have n elements come into our sorting algorithm, we need to have at least n factorial. You could have more, right? But you need at least n factorial. Okay, so that's something, a nice property. Now let's go back to the tree for a second. If you think about what's going on in the tree, actually I'll draw it a little bit smaller. You're making a number of comparisons, right? And your tree may or may not be balanced, like the one that's up there at the moment. It's not quite balanced, but you might get a balanced tree. And the worst case behavior will take you, look at the tree we've got here. They're actually we've got here, there's a best case and a worst case. What's the best case that happens? The one on the right, the one on the docam. How many comparisons? You can get to the leaf in 2 comparisons, right? But the worst case, how many comparisons? 3, right? So something we haven't taught you yet, but we will come back to this, is that the longest root to node path through a tree is called the height of the tree, okay? So we call this h. Now, I hope that you buy the fact that, yes, we need n factorial leaves, and yes, the worst case path through the tree has height h. We can use these 2 properties to actually prove now that our lower bound sort comparisons is n log n. So let's see how this works. All right, so I'm missing a sheet of paper, and I don't know how it happened. And it's the one I need. Did a piece of paper go flying off the desk? Or did I pick it up? Maybe it's on the back of that one. Okay, anyway, let's do this. So basically, what we know is that 2 to the h has to be at least, so let me rephrase. Okay, so this is what we're going to try and prove. You need to have a height of 2 to the h to get to the bottom, And that has to be at least as big as the number of leaves you have, and that has to be at least as big as n factorial, okay? So what we're trying to do is show here that basically 2 to the h is bigger than or equal to, greater than or equal to n factorial. So how could we proceed here? What do we know about powers of 2? How do we get rid of them? Because I want to solve for h. I'm not interested in 2 to the h. I want to solve for h here, because h is the worst number of comparisons through the tree I need to make. So how can I make that 2 go away? I can take a log, right? So that's nice. I can then rewrite this. 2 to the h greater than or equal to n factorial means that, and I need to be careful with equals here, greater than or equal to what? Log 2 of n factorial, right? Do we agree? That's just log laws. Get the math cheat sheet. Now, what do we know about log? Well, actually, let me write this again over here because I'm going to run out of space. H is greater than log 2 of n factorial. What do we know about n factorial? What does it mean? How could I rewrite this? Well, n factorial is n times n minus 1 times n minus 2 times blah, blah, blah times 1, right? Happy with that? All I did is expand the n factorial. Now, I can do something else here. What do we know about multiplication within a log? Get the math cheat sheet. What can we do instead? I see people doing this, and I like it. Yeah, that to this. So that's sum. You can take multiplications out and sum them instead. So what I'm going to get here is log n plus log n minus 1 plus blah, 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 plus log 2 of 1. I know it doesn't, it's 0, it doesn't matter. We can stop at 2 if we want. Okay, we're making progress. This is nice. Now let's make an observation, and I'm going to try and trick you. And I've told you I'm going to try and trick you, so let's see what happens. How many terms are there in this expression? How many terms are there in this expression? There are n terms in this expression. What is the largest term in this expression? It's log n, right? So do we agree that the thing in pink here that I've underlined, and I'm going to mess up the math here, but because I have to write it, but this thing here, I'll write pink thing. Sorry, it's bad. Is less than or equal to n log n. Do you agree? Right? Because the biggest term is log n, and I've got n terms, but actually n minus 1 terms are smaller than n, so that has to be true. Have I actually proven what I've set out to prove? How did I trick you? What is this? This is actually an upper bound, right? This is an O of n that I've just given you. Sharp, nice. Shouldn't have told you I was trying to trick you. So I've actually not yet shown this. I've actually shown a big O. But luckily for me, it's kind of pretty easy to get from this to a lower bound. So what I can do instead is a similar observation. So I'm going to go back here. I'm going to say log 2, and I probably just should stop writing log 2 because it doesn't matter. Log 2 of n factorial, we just showed that that is less than or equal to, sorry, n log 2 of n. But we don't want that. We actually want something smaller, because all we know is that it can be as big as log 2 of n log n. But we actually want to show that it can't be smaller than n log n as well. So what we can do here is, I'm going to draw a line, start doing something different. Log 2 of n factorial, and I'm going to rewrite the pink thing, okay? Log 2 of n factorial is the same as log 2 of n plus log 2 of n minus 1 plus blah, 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 plus log 2 of 1. Now, what you can observe is that if we took the first n over 2 terms, right? Does anyone see where I'm going with this? I took the first half of this. Then what I can say, for sure, is that log 2 of n factorial has to be greater than, I'll put a greater than equal to hedge my bets, but I'm going to say greater than n over 2 log 2 n over 2. And the reason I did this is because if I threw away the bottom half of this equation, I just said I don't care about those sums, get rid of them. Well, I know that the last term that I left was the n over 2 term, right? So there are n over 2 terms in the half of the equation I preserved, and all of those terms are greater than or equal to n over 2, so this actually holds. So I know that log 2 of n factorial has to be greater than n over 2 log 2 of n over 2. Now, in our asymptotic applications, what do you think this is? Do we care that it's n over 2? No, it's still n log n, right? So now we get n log n because this is bigger than that, right? Question? I'm not sure I entirely get the question, but maybe can you come in the break and we can hash it out? Yeah. I'll leave it as it is. If you find a mistake in the proof, I'm very happy for you to fix it. I'll upload this document so we can have a better look. But yeah, so there's possibly a very good observation. I don't know yet. Okay. So this is actually a textbook proof. If you wanted to cheat and you didn't want to do it this way, there's something called Stirling's approximation. And you can essentially say, hey, I know that log 2 of n factorial is n log n by Stirling's. I don't need to do any other work. If you're lazy, you do that. But has anybody in the room seen Stirling's before? Yeah, so one person. So you're allowed to do it and no one else do it and no one else is, okay? So hopefully now you agree, and again, I've got the slides here, so maybe you don't agree, but at least it gives you something to think about. The number of comparisons, these are just for me to fill in, so I've already told you all this stuff, don't worry that I'm skipping through. Here's what it looks something like. Basically, you're bounded by n log n. So that means any correct sorting algorithm, worst case, has to do at least n log n comparisons. So that's really nice, because it means that when we implement a merge sort, it's kind of optimal. Like, there's no point of us spending more time to try and make sorting algorithms better, because we're kind of already there. We do the optimal number of comparisons. What am I going to talk about next today, you ask? Let's make sorting better. Let's not do any comparisons. Does that sound interesting? Maybe? How could we possibly sort without doing comparisons? comparisons are the way we sort things. Does anyone have a galaxy brain insight for us that we might use? Anyone that looked 2 slides ahead in the lecture slides that they're looking at right now on their computer? How can we possibly sort without comparing stuff? Yeah, how? Well, that's an interesting question. You're preempting material from week 5 or 6. We will come back. So there was discussion here about heap sort. Heap sort uses a data structure to sort, but heaps actually do comparisons internally. But the idea of using a data structure to sort stuff is a nice idea, and that might be one we can apply here. Yeah? Well, that sounds terrifying. You could randomly put stuff together until it's sorted. You may have seen that somewhere before. Yeah, but to tell it's sorted, you still want to have to do some comparisons. But yeah, maybe that's a comparison-free way. I mean, at least the sort itself isn't doing comparisons. The check at the end is, yeah? Get a quantum computer? Yeah, these are fantastic ideas that I don't know how to do. Delete stuff till it's sorted. Wow, you guys are super creative. I love it. Oh, I love that. That is actually perfect. Yeah, so make a gigantic list that's empty, a giant array, and if you see element 3, put it in the 3 index. If you see element 10, put it in the 10 index. Just put everything in the index, and then walk the array in order, and you've sorted it. Wow, that's a really galaxy brain idea. Did you look at the slides, or did you come up with that by yourself? Oh, that's awesome. Okay, yeah, so maybe some ideas, but that's really nice. So let's look at an algorithm called bucket sort. So it's exactly like I said. What you're going to do is take some input. Now, you're already thinking, hey, hang on, there are problems with this. Yes, it's not perfect, so we're going to get to that. Let's suppose you've got a list S, and it has n key element items. They don't have to be key element items, but it's easier to reason about. And those keys are in the range 0 to big N minus 1. So we've got a big N here. You need to be able to differentiate between small n and big N. Okay. So what you do is use the keys as indexes into some auxiliary array of B lists. We call it like a bucket array. And so the first phase of the algorithm is go through each entry, find which bucket it goes into, and put it there. Now, Has anybody thought of a potential issue already? For example, yeah, what is it? Yeah, you're going through an array, so that is O of n, but that's okay. I mean, it's still better than n log n, right? Yeah? Duplicates. What if I've got 3 7s? Well, yeah, okay, so it doesn't matter, they're already sorted. So there are two parts to this question. One is how do we handle duplicates? Clearly, if a bucket can only hold one thing, we're in trouble, because if we strike the bucket and there's already something there, job done, we're buggered, right? But we can have a list of lists, right? The bucket could be a container itself, so we can get around that. Now, the other observation is one we're going to get to in a second, but it is essentially, can you treat this 7 the same as this other 7? Are they the same or are they different, right? And we'll see this. Yeah, we'll see this in a second, so that's really nice. Basically, once you've got the bucket, everything in its bucket, you just walk the buckets, walk the elements in the buckets in that order, and out comes the answer. So suppose here, look, I don't know what's going on with the graphics. There's some weird stuff. I don't know what this is, for example. It's just a list. So you've got a list that has 7A, 1C, 3A, 7G. The characters are just like data payloads that we don't care about. We're sorting on the keys, right? So what bucket sort will do, and I guess I can show you, like, instead of going to the example. So we look at 7. 7 goes into the 7 bucket, right? So now I've got like 7B here. Then I'm done with that one. 1C, so I go to 1. I put 1C here, done with that one. 3A, do you see what I'm doing? Makes sense, right? So the only kind of interesting thing is if I get a duplicate, here comes a duplicate, 7G. I'm going to go to the 7 bucket. There's already something here, so I have to put this one afterwards, right? Or I could put it before, but we'll come to that in a minute. 3B, go over to bucket 3, which is here. 3B, 7E, so I'm going to get another 7 here, right? Now, am I done? Am I sorted? I have something else I need to do now, right? So that's phase 1. I'm putting things in their buckets. Have I compared anything yet? No? So that's cool. That's... this one. So phase 2 is stop. So now I'm going to walk across the buckets like this. And for each bucket, I'm going to look inside. And if there's stuff, I'm going to traverse down that list as well. Okay, so I'm going to go, there's nothing here. Come back up to the start of this one. Here's 1C, so output 1C. We'll put it in another list. Then come back up. There's nothing here. Come back up. Okay, I've got a 3A, I think. I can't read my own writing. I've got a 3B. And then I come back up, empty, come back up, empty, come back up, empty. Come down here, 7D, 7G, 7E, and then empty, empty, done, right? And here, if you were better than me and got this drawn in one list, that's even better. But that list is sorted, right? You sorted the list. Is there any issue here? What if you, yeah? Yeah, okay, that's a really, really nice one, yeah. So, yeah, great, that's perfect. So that's one. And there's something else secondary going on here, and I know it's hard when I'm saying stuff like this because I'm trying to get you to possibly say something that you don't know what I'm trying to get you to say. Any other observations here? Yeah, so each bucket has an array there, right? So when I draw those arrows vertically down, that's just like another array or perhaps a linked list or something, yeah. Yeah, so that's a nice insight. So what if I also wanted to sort on D, G, and E? The 7s aren't sorted with respect to each other, right? They're sorted with respect to the order that they came in. They're preserved in that same order. Now this is an important concept. It's called stability. It'll come up on the next slide. But that was the key observation I wanted you to make here about the stability of the items. So that is, right, just to repeat, because I saw this 7 before this 7, and that one came before this 7, they are preserved in that order. Whether or not that's sorted, we don't know, but they're preserved in that order, okay? So there's a sketch of what happens. Now we had another really nice insight here, which, and here's the algorithm. Let me go ahead. Okay, so here's the analysis. Spoil it for you. But we had a really nice insight in the front here, which is, well, what happens? I mean, think about this. You can see that you need a bucket for every possible key you've got, right? What if your biggest key is gigantic? What does the array look like? Gigantic, right? So if I gave you integers in the range 0 to 50, well, that's okay. I'm happy to allocate 50 things and put some lists of lists. What if the biggest integer was like 2 to the 64? You're going to have a gigantic array, right? So that's one of the problems here. the pseudocode's very simple. It's pretty much exactly what we just did. I've got real Python code for bucket sort too. I'll share that after the lecture. We might look at it if time permits. But I'm going to move on here because I want to get to more interesting things today. So stable sort is what we just discussed. The relative after the lecture. We might look at it if time permits. But I'm going to move on here because I want to get to more interesting things today. So stable sort is what we just discussed. The relative order of any two items with the same key has to be preserved, okay, with the execution of this algorithm. If they are not preserved, it's not a stable sort. So you might see sometimes people say, is sorting algorithm X stable or not? That is this property. The stability means that the 7D comes before the 7G, comes before the 7E, because that was the order of those in the original input, right? That's all stability means. So let's think about an extension to bucket sort. We can actually think about some data, different types of data, as tuples, right? Now, a tuple is essentially just some n-dimensional representation of something where each dimension can be compared to other objects in the same dimension, right? So, for example, coordinates in space could be a 3 tuple, like if you had x, y, z, a, and you had b, I guess, and a different x, a different y, and a different z, you can compare them on their first dimension, and if those dimensions are the same, you can compare them on the second dimension, and if those dimensions are the same, you can compare them on the third dimension, for example. So essentially, you can sort things like this. Same with characters, same with words, right? Ant versus apple. The A's are the same, so we look at the next character. N happens to be less than P, so we know that ant comes before apple lexicographically, and we're done, right? This is just an idea of, this is just essentially generic comparisons, right? You can make generic comparisons with this lexicographic ordering. So if you have 2 D tuples, right, 2 tuples of dimension D, you can compare them recursively, basically on dimension 1 and then 2 and then 3, and all the way until you find a mismatch. If you don't find a mismatch, they're the same. That's all it says. So this is just fancy weird looking math to say, let's compare the tuples by their first elements, and then by their second, and then by their third. So in this case, and I've sort of misled you here, I'm saying, hey, the tuple 214 is less than the one 325 because 2 is less than 3. The tuple 214 is less than 225 because the 2 and the 2 are equal, so I look at the next dimension and I see that 1 is less than 2, so therefore this one is smaller, right? And then 214 is less than 215 because the 2's are the same, the 1's are the same, but 4 is less than 5, right? That's it. This is just a snooze. I can see people sleeping. So basically, that's lexicographic order. Now, the cool thing is that you can apply this. This is called tuple, right? That's it. This is just a snooze. I can see people sleeping. So basically, that's lexicographic order. Now, the cool thing is that you can apply this. This is called tuple sort. You can apply this to any. You can apply this idea to anything that you can compare lexicographically. So all you need is a comparator that compares 2 tuples by their ith dimension. And in fact, some of you would have implemented comparators like this. If you've got an object that has multiple things inside, you might compare on the first thing and then the second and so on. You need a stable sorting algorithm that uses that comparator, so we know what stability is now. And what we do is basically just call this stable sort in a loop once for every dimension, right? So here's our algorithm. Go through the dimensions from the biggest one to the smallest one. Biggest one has precedence. And call the stable sorting algorithm on the tuples of that dimension. This is actually not even a kind of a real sorting algorithm. It's just a sketch for a class of sorting algorithms, really. But the cool thing about this is that it runs in dimension by t of n time, where t of n is the running time of your stable sorting algorithm. So if you can implement a stable sorting algorithm in linear time, this is going to run in d times n time, which may or may not be good depending on how big d is. If d is small, that's going to be like a linear time. If d can grow really big, then it's going to become kind of n squared feeling.
Why isn't this also a comparison sort? Because instead of comparing 2 things together in the list, you're just comparing the 2 places.
Yeah, I would say that this is a comparison-based sort. We're still, so the question was, hey, hang on, we were talking about comparison-less sorting, and now you're saying let's compare dimensions. We are comparing, yeah, but we're getting to something a little more interesting. And so this is a sort that we don't really know what happens inside stable sort. Perhaps stable sorting is bucket sort. So that would be comparison-less, because you could use bucket for the things in each dimension to sort them, right? As in, implement this algorithm, and when we see stable sort, put bucket sort there that we learned on the last slide, and you've got a comparison-free sort. If you want to put stable sort as something else, I will incriminate myself and make a guess that selection sort is stable. I don't even know. I don't think that's true. But basically, if I use a comparison-based sorting algorithm here instead, of course, then it would be using comparison. So very nice point. But what I want to get to, and we'll have a break after this one, is radix sort. Now, who's heard of radix sort before? A couple? Yeah, cool. So radix sort is an interesting one. It's basically a specialization, and this is, you just preempted this idea, actually, where you use bucket sort as your stable sorting algorithm in each dimension, and that way you don't need to do explicit comparisons, right? So that was the idea we just had. And this is something you can run where you've got tuples with keys in each dimension that are integers in the range 0 to n minus 1. So if each dimension you want to sort on has properties that allow you to call bucket sort that we learned just before, then you can do a radix sort, right? Otherwise you can't. Now the runtime here, because we're replacing, you would have seen on this slide that we've got a t of n here, and t of n is the running time of stable sort. Well, if the stable sort is bucket sort, the running time of bucket sort is n plus n, and therefore this thing runs in dimension times n plus n, right? Something I skipped over. And I'll give you a break after we talk about this. When we did the analysis and I just left it up and let you have a quick look at it, where does the bucket sort analysis come from? So if I go back to bucket sort, why is this the case? Why is it n plus big N? Where does the first n come from? Yeah, exactly. So the little n comes from taking the initial list and going through each element, right? That's a linear pass on the input list to put them in buckets. And the big N is traversing across the bucket array, which could be of different size, right? Which is why we distinguish them. Now, another way to think about this, and someone pointed this out last year, is that actually, if I don't know how big N is in the first case, well, the first thing I have to do is a pass through to check the data, right? To see what the biggest key is. So that's a linear pass. Then I have to actually create an array of buckets that's that big. How much does it cost to create an array of buckets, size n? Oh, of n, right? It's linear time to create an array of size n. So that's another big N cost. So I've actually already paid n, little n, plus big N before I've done any work, right? Because then I have to go through little n things again, putting them into the buckets, and then I have to go through big N things again to get them out of the buckets. So actually there are some hidden constant factors here, but of course you've all been taught to not worry about constant factors, right? But this might be something interesting that we come back to later when we talk about these in practice. So let's have a 5-minute break. I want to finish on time today. It's 2:54, so we've got under an hour, and we've still got a bit of stuff to get through. So I'll give you like 4 minutes-ish, and then we'll keep going, okay? Oh yeah, cool. Yeah, actually, what I'm going to try and do, I'm going to have a quick look at what I've got left and see if I can fit it in. Because this algorithm I'm about to talk about actually involves you getting bits out of numbers. And so what I've got, and I'll upload it if I don't get it, but I'm thinking what I'm going to do, is I've got a little script that says, hey, what if I want to get bits out of integers? How do I do that? You know, remind you of how bitwise operators work and stuff. That'll give you a pretty good hint as to what to think they should do. Yeah, so hopefully that'll help. But if not, I'll be around for an hour after the lecture in office hours if you've got time. You can always swing by and I'm happy to sort of help you out. Yeah, that's okay. Can you make the help session? Yeah, 2 to 4 tomorrow. I think it's in Priestley, so apprentice. I always get those buildings and stuff. But nearby, yeah. So if that doesn't give you the kick you need, come in tomorrow and we can help you. Awesome. We'll ask one Ed. We can try it. Yeah. Yeah, if it's within a word. If it's within a word, yeah. But remember that your word size is 64. So if it's within 64, that's possible. But if you're shifting across like 1,000 bits, Python actually lets you just throw it. It's not going to be constant. But you're going to assume 64 bits because that's what it's called. So yeah, you'll get close to Python. No, they're not. They won't be on board. So you'll see. When you submit, you'll see if you fail something, and you'll see maybe like test exceeded time. For which one? Like, oh, do you mean expected time again when we're looking at Oh, imminently. Yeah, probably tomorrow. Yeah, probably tomorrow's not Monday. We're testing the test a bit more because the API changed and stuff. We set us back a little bit. I think it was for the greater good, but it's still easier. So yeah, we need to just double check. Of course, we can update it, but it's better to. Yeah, of course. I know. Yep. Yeah, I know, and I hope people fix it themselves because this is also the reason I haven't fixed it is because the lesson is right here on test. Actually, the one of the other tests is wrong too in the Waller. The output asserts for 0, but should be asserting for -5. People don't realise, or they don't try and write their own. They're going to not realise that this is so trust nobody. But thanks for letting me know. Yeah, no, I do know that, but I just yeah.
I don't think so. Treating raw base with an main concept, dropping into treating raw base with an X concept, that would bring it to a different cost. So the way you would do that, I think, is by
okay.
So I'm not.
I see your point. Yeah. It's funny. Logs are where things often go wrong, and they're often where computer scientists are like, I don't care, it's log 2. Like, I just ignore everything else that happens in the web. But yeah, you're probably exactly right. So I need to be a little bit careful with this. But I think the framework of the proof is. I think that probably that's just a bit of a. Yeah. So sure. Did you see right at the start of the lecture? If you do, be very careful that it won't possibly break out there. But if you do, and there's default arguments, it should be fine. But my preferred solution would be you'd add a secret function that does what you want to call it from the one that's public.
And the user that is
It won't matter in your case because we're not going to get at your API publicly. But I think double underscore will give you the name enabling, which means anybody trying to use that function on your object won't be able to call it.
Okay,
so I think double underscore is what you actually want.
Am I allowed to, like, is there a type of things that are indexable? Because at some point I end up using the self-indexing and like indexing in the same kind of things.
But we can bracket is the type dynamic. No. Yeah. That's why stability is important. I'm about to talk about it. Yeah, so hold on, but if it's still unclear again, come back and we'll go through it again. Good question. All right, guys, let's keep going. We've got a lot to get through in a short amount of time. Okay, so radix sort is another algorithm that we can use, and I've actually implemented radix sort, and you're going to get an implementation. So don't sweat if we don't get to the code on the computer. I might get ahead to the data structures instead. However, I'll explain how it works. So what you've got coming in is a sequence of b-bit integers. Now, when we use integers in statically typed languages like C, often they're basically 32 or 64 bits, for example. In Python, things are a little bit weird because ints can be essentially unbounded in size. But what you do is you have you can think about a binary number as say 64 bits, and of course, if our number was 0, they would all be zeros, right? And I'm talking about unsigned integers here because in signed integers, the last bit is used to determine whether it's a positive or a negative. I don't care. I'm just going to use unsigned int. So now all binary numbers will use the same size. It could be 32 or 64, but in our word RAM theoretical model, we just say it's a word, right? We don't really care. So what you can think about is that essentially a binary number is just another type of tuple, right? A tuple of b dimensions, where b is the number of bits you have, so 64 dimensions. So of course, we could actually do a bucket sort on those 1 and 0 values, striping through the integer bit by bit until we're sorted. So if I was going to think about it like bucket sort, you already learned bucket sort, how many values can a binary number take on? 2 values, right? So how big would the bucket array need to be for a binary radix sort? 2, right? The bit's either 0, it's off, or it's 1, it's on. Does that sound a bit more attractive than gigantic array that we might have needed before? Please nod, yes, sounds better. So the idea here is that we're going to run in O of B of n, and essentially it's just the same as bucket sort, but you've got two buckets, and the buckets come from looking at the bits in the number you're sorting. That's all. Now, you might not remember how to get at the bits of a number, and so I've also prepared something for you, which is, please remind me how bitwise operations work. Probably very helpful for your bit vector in the assignment if you haven't implemented it yet. So we'll see, maybe we'll get to that, maybe not. Now, someone in the break actually just asked a cool question. It was like, but hang on a minute, if I radix sort on the bits, things might end up in the wrong order. Like it might, what if I sort by this bit, but then on the next pass I sort on the next bit, it might mess up the ordering of the last iteration of the sort. So this diagram is going to show you why this works. And again, it's the stability property that we need. So what we're going to do is we're going to start at the least significant bit, which is the one that represents ones or zeros, right? So remember in week 1 when we counted in binary and I flipped you guys off? Remember that the rightmost bit is the one that represents 1 or 0, and the second one is 2, and 4, and 8, and 16, and so on, right? So we start at the least significant bit, and we're going to sort these according to bucket sort. And what that's going to do is say, get these 2 out, and then get these 3 out. Now, what you notice about this, and again, stability, why is it important? The first one is this one, the second one is this one, the third one is this one. So you can see that we're preserving stability here. We're doing a stable sort, right? Bucket sort is a stable sort. So we do that on the first, and then the second index, and then the third index, and then the fourth index, and magically at the end, I have sorted my numbers, right? So that's pretty cool. That's all radix sort is. So if we had our original bucket sort with a bucket array, we're going to be doing O of n plus n work, and indeed O of n plus n space, right? This is the bucket. This is the original sequence. So if I gave you numbers, 10, 99, 3, something that I don't know that's big, and then 20, bucket sort would require this much space, right? Because my biggest key is a big number, so I'm going to have a massive array with lots of empty stuff in it. Otherwise, I could do a binary radix sort, looking only at each bit being a 0 or 1, and I'm only going to need 2 buckets, right? So that's pretty nice. The other thing I could do instead is observe that if I've got 64 bits, right? That's 64 numbers, or ones or zeros. Actually, I don't need to go through bit by bit by bit by bit. I could actually take a byte at a time, right? So I could do a byte-wise radix sort. So in a case of 64 bits, how many bytes would I need to do? How many bytes are there in a? How many bits are there in a byte? 8. So how many bytes are in a 64-bit int? 8, because 8 8s is 64, I think. We're second and third years. Do we agree? Yeah, I think so, right? So what my point is instead is that you could actually do this with a byte instead of a bit at a time. Now, if I use a byte, how many possible values can a byte have? 8 bits. What's 2 to the 8? 256. So my bucket needs 256. My bucket array needs 256 indexes, 0 to 255, right? So there's clearly a trade-off between, the point I'm making here is in practice with these sort of algorithms, there's a clear trade-off between the number of buckets you can allocate. 256 buckets is no big deal, so doing a byte-wise radix sort's okay. If I did a byte-wise radix sort, if we go back and look at the algorithm, how it works, I go around here b times. So if I did a binary radix sort, this loop's going to go around 64 times, right? 1 for each bit. If I do a byte-wise radix sort, this loop's going to go around 8 times, right? But the 8 times it goes around with a byte-wise radix sort requires more work to be done at the comparison stage. So there's a trade-off between essentially the size of the buckets, the number of things that will end up in them, and the amount of work done, and what the right thing to do is really depends on your application, okay? But the point is you can do byte-wise radix sort. Does that all make sense? It's pretty simple. All right, I'm going to keep going, but I'll come back. We'll see. We might get some computer time at the end. Now, who knows about arrays? I'm not continuing until everyone puts their hand up. So you've probably used an array before. Now, a general array, well, we'll talk about linear structures, but these are sequences. So you've come across sequences before. Basically, a list, an array, a linked list. You put an element in first, hello, and then you put another element world, and so the first element's hello, the second's world, you're storing a sequence of elements. You're going to see lists today, you're going to see stacks, queues next week. Vectors is just a fancy name for extensible arrays or lists that are dynamic, or your assignment dynamic array, for example. We saw a static sequence in the first lecture to kind of explain to you what an ADT is. Remember, that's just a template for a data structure. We don't tell you how to implement it, we just tell you what operations we'd like you to support. So this is a static sequence. You want to be able to build the structure, tell me how many things are in the structure, get something out of the structure, or set something that's in the structure. And reminder from week 1, this whole course is about, given this API, there could be lots of different ways to implement it. For example, I could implement that as an array or a linked list, or perhaps a tree even, right? So there are different things we could do. Today what we're going to talk about is the dynamic sequence. Now the only difference is that we add to our API, we add an add function. It's an append basically. So what I want to be able to do is not just get some initial set of things and store them in an array. I want to be able to add stuff as well, add new stuff, right? So if you've ever used a Python list, you're using one of these already. Now, when we implement linear structures, there are kind of 2 approaches we can take. Something really funny happened last year in the course. We got to about week 11, and this guy came to my office hours, and he was really disappointed. And what he said to me was, and this is quite innocent, he said, "Sir, you taught us about arrays, and you taught us about data structures where stuff's contiguous. It's all stored together in a slab of memory. And then you taught us about lists, like linked lists, where you've got a thing here, and it points to a thing here, and it points to a thing here, and it points to a thing here. Is every data structure just one of those?" So he said. But of course it is. You can either only store stuff contiguously in a slab of memory or in different parts of memory. And this guy was super disappointed. He'd learned all these cool data structures, but they either used linking or they were in one part of memory. And I don't know what he wanted. Yeah. Yeah, so the question, so what I'm actually talking about here is a bit more of a lower level concept, right? So the question was, if that's true, why don't we just either use arrays or linked lists for everything? Now, the point I'm actually trying to make is not about the data structure that is an array that stores stuff contiguously in memory and we use it. It's more like if you want to build a tree is a type of structure that has pointers to places, or it could be stored, you could implicitly store a tree as a contiguous slab of memory. They're your only 2 choices. Either stuff is scattered around memory and it references to different parts of memory, or it's all jammed together in a slab. You can't do anything else. So that's kind of the point. So don't be sad when they're the only 2 ways you can possibly implement data structures. That's the only way you can use memory. Okay, that's just a fact. So if we're thinking about a static list, we must know the size at creation, right? This static list cannot assume new stuff. We get constant time random access, which is really nice. If I've got an array of 100 things, I can easily get any of those 100 elements in one operation. But what if we want to insert something? What if we need more space, right? So if I had a cool array with 4 spots, A, B, C, D, I can get at any of those elements in one operation in the word array model, right? You've all used an array. But in the static example, if I want to add a new thing, I can't do it. I have to make a new array of one thing bigger and copy all the stuff down. Now this might sound a bit familiar. So imagine you've got an array, and here you've actually got an array of pointers to other addresses in memory, perhaps. You've got some cities. You want to add Canberra in, and you want to keep the list sorted, I suppose. So you put Canberra somewhere in memory, you shuffle all this stuff down, you put Canberra in its place, and now your array looks good. How much does that cost? What do we feel about that? What's the worst case? Of n, right? Why is it of n? Yeah, because that shuffling operation might cost n, right? Worst case is I want to put something in Brisbane's place at the start. I have to move everything down. And the reason suppose, for example, this array wasn't sorted. I didn't care about order. What would I do? How much would it cost? Well, if I had space, I could do it in constant time. What would I do to insert something in this list if I had space and I didn't care about sorting? What would I do? Just bash it in the end of the list, right? Just put it there, and who cares? Okay, so start thinking about this a little bit. But think about arrays. Accessing an element by index is constant time. And remember, this is always true in our word array model, that we're our theoretical model of computation. Iterating over the elements of the array will cost you linear time. You know this already. Inserting or deleting an element, worst case, will cost you linear time, right? And memory usage will be linear. Now, you might want to think a little bit about why insertion or deletion could be linear time, but the idea is that we want to keep everything together. We don't want holes, right? So if I had an array A, B, C, D, E, and I wanted to delete A, I don't want that to be a null spot. I want to shift everything back, right? So hopefully there you can see where linear time is going to come from. You're going to have to move everything back, right? And I guess just to finally, before we move on here, the reason that I'm shuffling back and not just putting E here is, remember, we're talking about a sequence. So if hello is the first thing you insert and world is the second, I expect that order to be preserved in the sequence. So just putting world at the front and getting rid of whatever else was there, or messing up the order, that doesn't obey the sequence data structure that we're trying to implement, okay? So linked lists. Who's had fun with linked lists already? Who's had immense pain with linked lists already? Yeah, so simple, yet so deceptively annoying. Well, okay. The comment from the fair comment from the audience, your colleague said, especially annoying when someone changes the code in the API. Yes, I'm very sorry. That was a hard decision. I think it was for the greater good, but yeah, fair enough. Yeah, fair enough. You can all throw tomatoes at me next time or something. So let's talk about linked lists. These are a concrete data structure. That means we're talking about the implementation now, not the interface. What you're going to have is a sequence of nodes and a head pointer, singly linked list. Okay, so a singly linked list has some structure, and that structure keeps track of the head, the first thing in the list. And because it's a singly linked list, each node just stores a pointer to the next element and some data itself. Okay. So when I say next in this diagram, what is next? What actually is it? When you say node.next equals other node, what are you doing? What is that thing? It's a pointer. It's a memory address, right? More or less. So these are basically location in memory of next thing. The point being that these are not necessarily contiguous in RAM. Okay. So what I mean by that, and this is the same thing. Suppose that you implemented a linked list in memory. How am I going to do this? Okay. How do we represent RAM in our word RAM model? How do we represent memory? Sometimes at the start of the first or second week, I was drawing these pictures. Basically a giant tape, right? It's just a giant array. Your whole computer memory is a giant array. So imagine that this is your giant array in your computer's memory. Now suppose you have a linked list that looks like this one. You've got your linked list object. It has a head pointer to some object. It has a tail pointer to some node. Each of those nodes points to the next one. The last one points to nothing, right? Now, this object in memory could be sitting here. So this is like your linked list object. Now, the first node in your linked list might be sitting here in memory. The second node in your linked list might be sitting here in memory. And your third node in your linked list might be somewhere up here in memory, right? And so when you say, I'm at this node, and I want the next node, you're somewhere here in memory, and that's saying giving you an offset to a different memory address that's earlier. So the point is, it's not contiguous, right? There are little chunks in memory with stuff stored in them, and each pointer just tells you where the next memory address is to go to get that thing. Does that all make sense? Yeah? Question? It's a really nice question. So in a singly linked list, do I need a tail pointer? Can anyone tell me what a benefit of a tail pointer might be? Yeah, what if I want to support an operation which is append, right? Append means put something at the end of the list. I don't have a tail pointer. How do I get to the end of the list? I go to the head, next, next, next. While next is not none, keep going through. Once I get to the end, stop, set next to the thing, I'm done, right? If I have a tail pointer, I go to the end and I put the thing there. So it's the difference between a constant time operation and a linear time operation, right? That's a fantastic question. And actually, this is called data structure augmentation. We're going to come to this in a bit. But the idea with augmentation, it's just the idea that if you're building a data structure, if you can store member variables of that data structure, like a pointer to the tail, that allow you to do something quicker, you should do it, right? You should do it. So you don't need a tail pointer, but how much does a tail pointer cost in memory? 64 bits, right? It's a pointer, it's 64 bits. Would you pay 64 bits to get constant time append over linear time append? Yeah, especially if your list has 100 million things in it. You definitely should pay 64 bits. Great question. Doubly linked list. The only conceptual difference here is that instead of just pointing to the next guy, you're also pointing to the one before you, right? Now, you're all very intimately familiar with a doubly linked list. Do I need to go into specifics, or do you kind of get the idea? You know what it looks like in Python code. If you haven't started the assignment, please do that. Is there a question? Yeah, so I think it is. This is the head, right? Yeah, so this is, yeah, so you're right. We should make this like a triangle, like a Dorito, because it means it's a different object. You got tricked, but yeah.
This is something I had like when I was working on this assignment.
Yeah, yeah.
Now, like you said, there's the advantage of having a tail, there's the advantage of having a head. Then why not have like pointers to each element? Like
Oh, nice question. Yeah. Okay. Yeah. Now you're thinking right ahead. So the question here was, well, hey, I can have a head pointer that points to the first thing. I can have a tail pointer that points to the last thing. Why don't I have a container of pointers to random places in the list, right? You could do that. You could augment your data structure with extra pointers, one that's like halfway or something, right? For example, and if you could use that to make things more efficient, absolutely. Yep. Yeah, so that's an interesting point. Okay, suppose you had a pointer to the middle element. The claim was, well, then I can get anywhere in n over 2. If I'm searching for an element and that thing's not sorted, I'm in the middle, I'm going to need to go n over 2 to the end, and if I didn't find it, I'm going to need to go n over 2 to the front. So it's still going to be linear time, so I may as well just start at the front and go on through to the back, or start at the back and go on through to the front. However, if you do have sorting, that might be very helpful, because if you can go to the middle and say, the thing I'm looking for is definitely behind me, well, then I only do n over 2 iterations back to the front of the list. So that's a really nice insight that might yield practical empirical benefits, but perhaps no theoretical benefits. So that's a really nice idea. You could possibly think about doing that. I don't think it'll help you in this assignment, but yeah, it's an absolutely nice idea. A different type, well, any other doubly linked list. I'll come to bugs in a minute, so we'll talk about some of your painful issues. But there's another type of linked list called a circularly linked list. It's just another variation on the same theme. In this case, the end node points back to the start node. You might be like, why would you ever want to do that? Suppose you had a fixed size buffer and you always like a queue, and you always want to fill up a queue. You can just keep walking that circularly linked list, putting something at the current position until you're done, right? So that's one implementation. If you're implementing a shuffle algorithm, for example, that might be something you could use a circularly linked list. I drew a sketch of memory already, so I'm going to keep going. Python looks like this. This is a singly linked list, but you've seen this. So here I've got a node, it has data, it has a next pointer. We set data, we want to be able to hold arbitrary data in our node. We also want to be able to get the next element. Our linked list here has head, size. Perhaps you might like to add tail, right? You can put whatever else you want here. Now that's true in your assignment. If you're worried about, hey, can I put another variable in the class? Yeah, absolutely, if you want. If it's going to help, you should do that, okay? You've heard it from me. You've got the license to put stuff in your constructor if you need. So benefits compared to normal arrays, right? You can access the head element in constant time. You can do that in an array too. Guys, come on. Not too much longer, I promise. Iterating over the elements is going to take you linear time, right? Memory usage is going to be linear time, linear space. But one particular benefit of a linked list, do I talk about this? Maybe not. Imagine you had a list, like an array, right? And you had A, B, C, D, blah, blah, blah. And you wanted to put some element here that was like K, right? So what I'm going to have to do is everything D onwards, I'm going to have to shuffle up, right, by position. That's going to cost linear time, basically. So I've got to do all this up and put the K there. But in a linked list, when I get to C, and I've got a pointer to D, and perhaps D has a pointer back, all I have to do is make a node K, set this to point here, set this next to point here, get rid of this bit, and then set previous of this one here. Oh, maybe I messed up. But you see the point, right? You can basically insert in any arbitrary location in constant time once you're at that location, right? So if I hand you a node and say insert some node to the next position, that's going to take constant time. Whereas if I gave you a random access to an index and said insert some element here, that'll take linear time. Okay, so that's one benefit of a linked list. Already talked about data structure augmentation, fantastic question before. Common bugs. Now you're listening. All right. So I've got a head pointer that points to some element. I've got a tail pointer that points somewhere. All right. And I've got kind of, I'll draw bidirectional pointers like this. So common bugs are things like, I'm going to delete, suppose I'm going to delete this element and I'm going to replace it with this one. So I'm going to delete the tail. So I'm going to update this pointer here, right? So now I've got the tail, but what have I done wrong? I've already done something wrong. Yeah, what have I done wrong? Yeah, absolutely. That's right. So the linked list object here that says here's the head, here's the tail, that's all good, right? If I say show me the tail, I get the right element. But if I've got a loop that says something like, well, current is not none, and I'm iterating across the list, I'm going to go, this is not none, this is not none, this is not none, this is not none. I shouldn't be able to access this. I deleted it, right? But I can access it because I accidentally forgot to update the next pointer of that thing. So if I didn't set the next pointer of that thing to none, that's one line of code. That's one line of code that you don't even notice you didn't write. Your whole linked list breaks. And now when you insert at the end, depending on your logic, perhaps this thing gets a node coming off it, right? And then you've lost it. It's disappeared somewhere because you say, well, my head's here, my tail's here, and where did that thing I put in there go? Well, it's hiding behind the other thing that you forgot to delete properly, right? So if you get stuck with a linked list, you sit down with a pen and paper and you draw a picture like this. And every time you update a pointer, you cross out the arrow, right? And I guarantee you're going to find what's wrong with your linked list in about 30 seconds, right? But you need to go and buy a pen and paper. I don't know if you have those anymore, right? You need to sit down and think about it like that, okay? Now, the last thing I'm going to do today, and we're doing okay, we've got about 10 minutes, so something I haven't told you is about lists that can grow, right? And we want lists that can grow because if you always have to allocate a fixed amount of memory in an array and put stuff in it, when you need to add stuff to it, you're going to have to pay a lot, right? So it's hiding behind the other. So if I didn't set the, yeah, absolutely, that's right. So the linked list object here that says here's the head, here's the tail, that's all good, right? If I say show me the tail, I get the right element. But if I've got a loop that says something like, well, current is not none, and I'm iterating across the list, I'm going to go, this is not none, this is not none, this is not none, this is not none. I shouldn't be able to access this. I deleted it, right? But I can access it because I accidentally forgot to update the next pointer of that thing. So if I didn't set the next pointer of that thing to none, that's one line of logic. Perhaps the thing I put in there go, well, it's hiding behind the other thing that you forgot to delete. Every time you need to do today, this can grow because if you always have to allocate a fixed amount of memory in an array to implement an extensible list or a dynamic array, for example. And what we want to do is, you've already kind of thought about this, if I want to insert something dynamically, obviously I need to make room for that element. The worst case is that I insert at the front, it's going to take linear time, right? Because again, if I want to insert some element at position I need to move everything position because you want basically move right in Python. But a Python list you can do it. That's an interesting thought. We could probably use a linked list, but in this case, I want everything to be contiguous in memory. I don't want to use links. I want everything to be next to each other. Oh yeah, okay, getting ahead. That's a really great idea. We could double the array size. So let's have a look at a couple of those strategies as the last thing we do today. What I'm interested in right now is a situation where I have a list. The list has some stuff in it, and maybe it has some empty space at the end. Okay? if I want to put something at the end of a list and there's empty space for it, what do? Just put the thing in the list. What are you asking me these sort of questions for, right? Put the thing in the list. Now, how did I know? How did I know where the end of the list was? How did I know to put the thing there? Yeah, should I be recording the position in my data structure of the last live element of my slab of memory? Yes, I should be doing that, right? So inside your data structure, you don't just have, extreme assignment spoilers coming. You don't just have a list here. You also have self._size, right? And size, well, let's make this I, is the last index containing an item, right? So if I want to insert something, I go to position I+1 and I put it there. But how do I know that I have space left at position I+1? What else might I need to track? Yeah, so I might also have something like capacity, right? And that's going to be how many things in total I could possibly store. So now you can see that if I have these variables recorded in my data structure, I can say, hey, the end element is sitting here. I've got capacity for this many elements. I want to insert something. If there's capacity, just increment the size and put the thing there, right? Sounds easy. It is. It's constant time. It's great. What happens when size and capacity are the same? What does it mean? Yeah, it means that my array, in my really great notation of this, right, it's full. There's no space to put something else. So now I need to take action. You need to take action with your dynamic array. There are two things you could do. You could increment the size of the array by constant, or you could increase the size geometrically. Now, one of those sounds fancier than the other. And I'll tell you which one you want to do in a sec. Okay? So here's what the code looks like. You're storing capacity and you're storing length. Basically, all you're saying is, if I get to a point where the capacity equals the size, as in the length, the number of things is capacity, I've got no space left, I allocate, so before I had a data pointer pointing to some slab of memory with stuff in it, again, using my notation, that's full. So what I want to do is allocate A prime to point to something that's bigger, right? So that's this. Well, let's call this A prime, so it fits with my notation above. We make a bigger array. We set the capacity of that to be, whatever it is, bigger, right? And then we go through all the things in here and we copy them into this one. Now look, I've got some spare space at the end that I left over. And then all I have to do is say, hey, now the array is here, right? So update that pointer to here. And this thing gets garbage collected and goes away. And life goes on and we're happy, right? Because now I've got space. I can put my thing there. Does that make sense? So that's just some keeping track of some variables. Indeed, I'm doing a copy. What's the cost of this part? Oh, n, right? Because if I've got n things in a full array, I have to make a bigger array. And then I have to pay n to copy those items across. Even if you're in C land and you do a memset, it's O of n time. You can't copy the stuff in less than the amount of stuff that there is, right? So this is a linear time operation. Okay? Then you update the reference to the list and you put your thing in the list. Life's good. This is exactly what you should be doing in your assignment. So the question is now, how much bigger do I make the list when it's full, right? And we had someone here say we should double the list size. Who agrees that that's a good idea? Why don't we just add a constant number of things to the front of the list? Who thinks that's a good idea? So I've got a list of, let's say I've got 1,024 elements. It's full. Why don't we add 10 more, right? We copy the stuff down. We've got 10 more inserts until we have to do another reallocation and a linear time op, right? So let me actually show you. Let's benchmark these. All right. Here's more spoilers. Sorry if you've already done the assignment, but you don't need this help if you're already this far in. And if you're not, here's some help. This is what a list might look like. A list might contain a slab of data with nothing in it to start with. We need some initial size, so I'm going to start with 4 elements, but maybe I'll start with 1024, right? Something with the power of 2 is something good usually. Computer scientists like powers of 2. I could put 7. Doesn't actually matter, but I'm going to use 4. Now, the capacity at the start is 4. I've got 4 empty slots. I've got nothing in here right now. Now, I've got 2 extension algorithms here. One is, if I'm full, I'm going to increase capacity by the constant, right? The constant here is 10. I'm going to add 10 extra things to the back of the array. Now, because the way memory works on a computer, you can't just ask for 10 more addresses after this one because something else might be there. You need a whole new array, right? Otherwise, we'll just be extending our array. So what we do is we increase capacity by constant. We make a new list of the new size. We copy the stuff across, and then we update the pointer to the list, right? And that's easy. That's all we do. Another thing I could do instead of adding a constant amount of things is I could triple the size, right? So if I had 4 elements first and I ran out of size, I could allocate a new array of 12 elements, right? And then if I ran out of 12, I could do, what's 3 by 12? Just kidding. Yeah, 36. I actually do know some arithmetic, guys. Just trying to be interactive. So the same thing, though. I triple the size of the array. I copy the stuff across, and I update the reference. Now, let's have a look at what happens. I'm going to run some code where we're going to append 100,000 things to this dynamic list, right? Now, what I'm going to do first is I'm going to do the extend by 10, okay? So each time I run out of space, I'm going to extend the array by 10 elements. And what I'm doing here is I'm appending which element I'm telling you which element I'm currently appending, and I'm counting the cost of the push. The push costs 1. It's a constant time operation if I've got space. If I don't have space, it's a linear time operation, right? So does this feel kind of slow, or does this feel okay? So what if instead, right, maybe I could make constant a bit bigger. Instead of adding 10 elements, let's add 100. Well, it goes a bit quicker, doesn't it? And that's not surprising because it means that instead of resizing every 10 steps, I have to resize every 100 steps, every 100 inserts, right? What happens if instead of doing that, I triple the array? Does anyone have any ideas what's going to happen? Right? Much quicker. So basically, and I'll show you the mathematics in a second if we get time, basically, there's a special type of analysis called, and that was meant to be more impressive, but the print statement's kind of slowed it down. But trust me. So there's a type of analysis called amortization. It's a bit tricky, and we don't go into it properly in this course. If you want to learn amortization properly, Comp 4500 will be where you learn that. But at the bottom, the intuition is chocolate. Suppose I go home and I go, wow, that was a great Comp 4506 lecture today. I'm going to treat myself to a box of Lindt chocolate and eat the whole thing. Seems bad, maybe, right? But if I don't eat a box of Lindt chocolate for another week, well, I can average out that cost of eating the whole box in one day to, well, it was only 3 chocolates per day across a week. That doesn't feel so bad, right? That's kind of the intuition with amortization. Now, if you add a constant amount of space to the end of your array when it's full, no matter how big that constant is, the math works out that it's going to cost you, on average, amortized, linear time per insertion. Per insertion. Who's freaked out? Yeah, sounds freaky, right? Who would pay? Who? Would any of you pay? Per works out. If you add constant amount of space to the end of your array when it's full, no matter how big that constant is, the math works out that it's going to cost you, on average, amortized, linear time per insertion. The math works out that it's going to cost you, on average, amortized, linear time per insertion. Per insertion. Who's freaked out? Yeah, sounds freaky, right? Who would pay? Who? Would any of you pay linear time for a single element insertion to an array? No. What's going on here? You get an insertion where you've got space, costs you O1. You get another insertion where you've got space, costs you O1. You're full. This insertion is going to cost you O(n), right? Now, because you're only expanding every constant number of elements, you pay n every constant number of things you insert, okay? So the amortized cost will be, each push is essentially costing you, on average, I've got 5 minutes, linear time, right? And that is extremely bad because we expect to be able to push something into a list, we should be able to append an element to a list in about constant time, right? Instead, if you decide to double, and it could be triple, it could be quadruple, it could be 1.5, it could be 1.6, as long as the growth is geometric, when your array's full, if you make your new array 1 point something bigger than 1.0 times bigger, as you go out to infinity, the time required per n pushes will be O of n. So if I can do n pushes in O of n, it means that each push, average, takes constant time. So if any of you give me a dynamic array that increases by a constant, I'm going to shake you because you're going to get linear time per insertion, but you want constant time per insertion. Now, there's a bit of math here. I think Skinner's way is a little bit more clear, and I put this in a lecture slide so you can go through. I knew I was going to run out of time. I put this there so you can go through in your own time. But basically, we do this analysis with powers of 2 because it makes the math nice. But again, you could make your array growth rate the golden ratio. You can make it 1.2. You can make it 10. You shouldn't make it 10. Why wouldn't you make it 10? That's the end of the lecture, but we've got 2 minutes and we're going to talk about that. So what's going on? Oh, yeah, so beautiful. So what's going on here is, I need a blank slide, but I'm going to just use here, okay? So this is important. At the moment, at the exact moment, you need to reallocate. How big of an array do you have? N, okay? I'm using n slots of memory. What do I need to do to get this into a bigger array? I need to make a new array, and if I'm doubling, that new array will be 2n, right? How much memory at this very instant in time am I occupying? I'm using 3n memory, right? If my computer, if I have an array that's half the size of my memory, can I make a bigger array anymore? No, right? So instantaneous space overhead is the thing that you're talking about here, and it's a very good insight. Instantaneous space overhead is the only reason you wouldn't want to do something as big as doubling. 1.5 times will give you the same benefit, but your instantaneous space overhead will be smaller. Now, that's always a trade-off, because if your instantaneous space overhead is smaller, it means that you have to reallocate more often, but you still get amortized constant time push. I'm just going to say that if you need to go, that's the end of the lecture, but I'll take a question. Yeah, so that's a very interesting question. Could you make exponential growth? Yeah, if you wanted to. But again, think about your instantaneous space overhead. If I've got a quarter of my RAM and I want to take some exponent of that bigger, right? Or like, because doubling is 2 to the n, right? It's a double. But imagine if it was something bigger. You're going to need even more space to allocate before you can copy, right? So doubling's the typical strategy. Great question though. Sorry I released everyone.
Some of the parts of the assignment agent to get from the smallest. Was the next lowest, therefore it
Hello, good afternoon, everyone. Welcome back to Comp 3702, Artificial Intelligence. Today, we're going to be concluding Module 1 on search and going through very quickly some of the parts of the assignment so that you can see that. Then we're going to start Module 2, which is on reasoning and planning with strategy. Right, in terms of this week's logistics, assignment 0, which is not worth any marks, but is there for practice for you, is due this Friday at 1 p.m. That mimics the due date of your future assignments, so you'll see kind of what happens if you don't submit. So with that closing, and then for this assignment, you can submit late, and you'll see it'll just come up with a little late tag on that. We will be closing the report submissions, however, because the purpose of having a due date for this assignment in particular is so we can provide you with some feedback for the report part. The code, you get instant feedback for that, so there's not really much point to a due date other than motivating you to complete it. In terms of the stats that we're at for you guys submitting to assignment 0, we have 238 code submissions and 139 report submissions, so that actually is looking really good. However, of course, I think we have just over 450 students, so there are still a lot of you, maybe not the ones who are here in the lecture, who have not actually completed this. This is a chance for you to practice your skills in Python, so as I mentioned before, it is strongly recommended. Another formative assessment is the Ripple rounds. Ripple round 1 is open, so that opened, I believe, last week, and that's on module 1, which is search, so that gives you a chance to do some practice. I've imported some modules there for you to practice as well. In terms of that, it's just a chance for you to create resources, moderate other people's resources, and then use those to practice your learning, and it basically gamifies learning using AI. Basically, it identifies the things that you're not as strong in and may recommend you certain resources. So that particular round ends in 10 days, so a bit over a week. Now, big announcement is assignment 1. So that's due in just over 2 weeks, and the support code for that has been released on the GitHub. So you would have received my Blackboard announcement with this link. It's also on Blackboard. So you go to github.com/comp3702, and it's the only repository that's public. So you'll see that there. There's a README document which provides details of this assignment, so what all the different files are. And then if you read within them, for example, the solution.py file, that's where you're supposed to edit the file and implement search. So what you'll see is there's a class called solver. You can initialize any variables you want in that solver, and then you need to implement UCS, uniform cost search, and A** search. One thing you'll note is that we require you to do A** search in a particular way to help with marking, where you explicitly compute your heuristic in a separate function, so that you call that function from your A* method. In addition, you can also have an optional method here called preprocess heuristic. So there might be some kind of preprocessing that you want to do before you compute a heuristic for a given state. Are there any questions with that? Who? Yep. Yes, there is a report as well. So the report will be, the first half will be basic understanding of search problems, so you'll basically be defining the components of search. That's basically what I wrote in my Blackboard announcement, that you should start by looking at the environment, what's the state representation, what are the actions available to the agent, and things like that. So it's very simple questions like that, and then the second half of the report is actually about analyzing the performance of the algorithms. The full details of that will be released on Friday when we finalize the autograder. The reason for that is that we just need to do some minor changes, and I think it'll be more confusing if I release an assignment and then modify it because some people might not, I don't know, see the announcement or something like that. In terms of what it looks like, who has had a chance to play the game? Not as many as I was hoping for. You should all play it. Like, I was hoping everyone here would have done that. It's actually a fun game. I'll show you what it looks like. So the environment is called bbot. So you have questions so far on the discussion board of how we should go about it. So please follow the instructions in my and added the children or the successors of that node. And we can see we've got these 3. Let's say the last one that was added was there. Who played around with my demos that I made, little PowerPoint slides? So they were in my announcement. Okay, so here I'm just going to go through a couple of examples. So here we have a 2D maze where we have some initial state and some goal state. So we need to get this agent to the goal. We're going to use this representation where E represents an expanded node and F represents nodes that are on the frontier. Right, so we start off and we take the first state, we put it in our frontier, then we straight away pop it off our frontier and explore it and expand it, and we get these nodes on the frontier. Now we're doing depth first search, so which of these nodes is it going to pick? They're all equal depth, so it's going to pick arbitrarily. So it picks the last one that was added, which happened to be that one there. So now we have expanded that node and added the children, or the successors of that node, and we can see we've got these 3. Let's say the last one that was added was there. So you can see all those F are on the frontier. So we'll pick one of the latest ones that were added. And you can see that's how search progresses in depth first search. Here we expanded, we got to a dead end, so we backtrack to the previous node and continue on to that frontier. And then we pop off the last node, do the goal check, it's the goal, therefore we have found our solution, and the solution that was returned was the following. What you can see here is that the way that depth first search selects the nodes from the frontier, it resulted in a solution that was not optimal. So it's not the solution that has the minimum path cost, step cost for depth first search, so each step counts as 1. Okay, so now we can compare that to breadth first search or uniform cost search with a 1 cost per action. They'll be nearly identical with a slight deviation based off the pseudocode that I'll highlight in these slides. Okay, so again, we start off with the initial state, we put it in the frontier, so that's a container that keeps the states that we're up to so far, and then we pop it off and we get the following. Now, we take, in breadth first search, the shallowest nodes. What's that called in terms of the container that we use for that? So is it first in, first out? Is it last in, first out? So it's the shallowest node. It's the one that was added first. So it's a first in, first out. Exactly like a queue. When you're waiting in line, usually, hopefully, the first person that was there gets served, and the next person, and then everyone else gets added to the queue. So you can see that's what happens here. We pop it off, we expand this node, and we get these nodes added to the frontier, and then we go to the shallowest node. So that was here, and we expand it, and we add those 2 Fs to the frontier. Same thing here. And this one just happens to be every single one. So I think I may have shown these last week. I just added the Fs in to make it a little bit more sense. So you can see what the search has just added and what's currently on the frontier to choose from. And so now here, there is a distinction between BFS and UCS, which I've added the pseudocode for. So the difference in when the goal check occurs, because in breadth first search, the cost is always 1. So if the goal state is already there, there's nothing else that could potentially be better. Whereas in UCS, uniform cost search, there's a chance that there's something still waiting there. Even though the goal is waiting in the frontier to be selected, there could be something else that has a shorter path. So here, breadth first search will take that node. As it expands here, the goal will appear in the frontier and a goal check is performed, and it will return that as a solution. In UCS, it continues on for a couple more moves and then gets to the goal state. So it's just a minor difference because the goal check is performed on node expansion. And both of those return the optimal path. In breadth first search, it doesn't look at how much each action costed. so it will just return the minimum step path, whereas uniform cost search will return the minimum path cost, but they are both optimal. All right, so now, today we're going to look at heuristics, and heuristics are some way that we can make the order of expansion of these nodes a little bit better, where we use some information about where the goal is, because that information is actually known to the agent. It's a fully observable problem. So what we can see is we could use a heuristic like the following. This distance here is called the Manhattan distance from New York, where you have to walk along the streets and avenues. So if you want to cross one block, you can't just go diagonally through the building, you have to go up and across. So you can see that cost here for every single cell is computed. So the goal state is here, so there's 0 cost there. There's 1 step here, 2 steps, etc. So here we can see if we're using greedy best first search with a heuristic equal to that. So here I just colored in the frontier in yellow. So you can see that when we explore or expand this node here, we get the following cells. So you can see 577. So which one is it going to pick next if it's only using the H function? So it's going to pick the lowest cost according to H. So that will be the 5, because 5 is the lowest out of 577. All right, so then it expands that. Now it's going to pick out of the nodes on the frontier, which is these yellow ones. So now it's going to pick one of these. So one of those arbitrarily, that picks the top one. Now you can see the 3 is the smallest, 2 is the smallest, 1 is the smallest, and then 0 is the smallest. And it turns out in this case, it was lucky that it actually returns the optimal solution. But what you may see is that sometimes that heuristic may be misleading and actually has no information of how far it's come so far. So that's where A star comes in, because it knows both how far it's gone so far in the search and an estimate of how far there is to go. So I've summarized those also in the second demo I uploaded to Blackboard, which gives the example of the UQ map. So this is another search problem, but this is already represented as a graph. And so your actions are picking one of these directions from a node, and the cost is here of that move. And here we have the heuristic values listed separately, so that is for each node what the estimate is from that state to the goal state. And so here I've got the pseudocode for what in Russell and Norvig is called best first search. I will never abbreviate that as BFS, otherwise that'll be too confusing. But effectively, it's how do you do search with something that we call priority queues. So priority queues are a type of data structure for our frontier, for our container, where we have our nodes that we're trying to pick from. You saw that in UCS, we prioritize the expansion of the nodes based off the path cost. For greedy best first search, it prioritizes it based off an estimate to the goal state. So that is all this function, f of n, which is that priority function. So you can see that, so it's called f here, and I call that f here as well. So this is pseudocode, and this is code in Python for exactly the same thing. So these match. All right, so to summarize the difference between the 3 algorithms that we will consider that use priority queues, we have uniform cost search, which what we saw is it basically propagated outwards kind of radially in a 2D grid. So we use the path cost from the root or the initial state to the current node n. For greedy best first search, we use an estimate called the heuristic, which estimates the cost from the current node to the goal. And in A star, we use a combination of both. So here we have an example of the costs. Whoa, sorry. So let's look at the node building 51. So that's marked here in yellow. So let's say it went, that node represents a whole path, and that path is from the initial state, UQ Lakes, via AEB to building 51. So if we were to look at each of these costs, so G of n and H of n, what would G of n, the path cost, be? So we can look at that. So from the root node, which is the initial state, we can see we've got a cost of 50 plus 15. So that's our path cost to building 51. And our heuristic is given in the problem definition. So that is 30. And for A star, we use a combination of both, so the path cost and the heuristic. So then we sum those together and we get 96. And that is what we use for prioritizing the expansion of the nodes for the different algorithms. Path cost and the heuristic. Our heuristic is given in the problem definition, so that is 30. The expansion of the nodes for the different algorithms. Here I've included an example of going through UCS. So please go through this in your own time. It's just a much neater version than what I write on my iPad. So basically, you have that starting node, you put it into the visited set. Then when you expand it, you take it off your frontier, and you get its successors or its children. And you can see we get A, B, and building 78. Now this is what we call the priority cost. So this here is in a container that we call a frontier, and in Python, that is a priority queue. So we can use various representations for that. In last week's lecture, I showed some very simple code that we designed our own node container, but you can actually use inbuilt things for this. For example, heap queue in Python. So that will take care of the picking of the nodes efficiently. So now, if we're using uniform cost search, our function is just the path cost, so how far it's come from the starting state. So we've got 50 and 70. Now which one gets selected? The lowest one, which is 50. So what we do is we run get successors on AEB, and we get the following 3 nodes. And then we put in the path cost of each of those, so 65, 65, and 60. What you can see is that we have building 78 again. Yep, sorry. Okay, so what you can see is when we expanded AEB, there's actually a loop where AEB goes to building 78 again. So if you look at the pseudocode, it does get added to this visited set or dictionary again. And what we do is we basically just replace the cost with the updated cost. So if you look in the pseudocode, if S is not in the reached set, or if it is already in the reached set, but the current path cost is less than the existing path cost, we replace it. So reached gets replaced with that current child. So that's exactly what I did there. And then we have the other ones. Then we look again. And here we take the lowest cost as the next one. So that happens to build things for this. For example, heap Q in Python. So that will take care of the picking of the nodes efficiently. So now, if we're using uniform cost search, our function is just the path cost. So how far it's come from the starting state. So we've got 50 and 70. Now which one gets selected? The lowest one, which is 50. So what we do is we run get successes on A, B, and we get the following 3 nodes. And then we put in the path cost of each of those. So 65, 65, and 60. What you can see is that we have building 78 again. Yep. Yep, sorry. It does get cost. We replace the lowest cost calculates AED. So then we take that off, get its children by the get successes method, and then we keep taking off the lowest cost. And now you can see here that the goal state appears. However, we don't actually get the solution until that node is expanded. So when it's selected from the frontier. If this is confusing, just follow the pseudocode. The pseudocode will literally step you through step by step. Okay, so now what do we do? We keep taking off the smallest, so 65. Turns out those children are already visited with a lower cost. Therefore, they don't get added to the visited or the frontier. Then we do the same thing again. Building 78 was the next lowest. Those nodes have already been added with a lower cost. They've already been visited with a lower cost. So you can see that here. And then that one. And then finally, we get to building 78. We do the goal check. So as we take that off the frontier, we run a goal check. We've got the goal. And we can then reverse this process to get the path. And we can figure out that we have to go this way, this way, this way. And we got a total cost of 50 plus 15 plus 40. So that is 105. And turns out that is the minimum cost path. Any questions? All right, so the difference between a blind search algorithm and an informed search algorithm is that in blind ones, you use no information about where the goal is. You just progress from the start, basically radially. In informed, you do use heuristics. So you use h of n, the heuristic function that estimates the cost from the current node to the goal in order to prioritize search. In general, informed search is faster than blind search, as you can see through those examples I showed. However, it's difficult to prove the properties that we described, such as optimality, completeness, and computational cost, as they depend heavily on the heuristic that you use. So here's a summary. So informed cost expands nodes with a function, f of n, that includes h of n. So it could be just h of n, like greedy best first search, or it could also include some other costs like g of n, as in what we'll call a star search. So you can see that in informed search, the nodes are selected based off this priority function, and that priority function must contain h of n. That's why it's called informed. And the 2 algorithms that we'll be covering are greedy best first search, also known as GBFS, and a star search. So as you saw in my animation that took way too long to make, with the 2D maze, we saw that expansion of the nodes. So here, I wish I knew before I designed the map that the UCS was going to go the wrong way. Actually, it makes sense that it would because it goes radially, but it literally went through every single node before getting to the solution. So you can see that the search progresses kind of out from the starting state outwards. So you can see that it's kind of what we call Euclidean. So it's a Euclidean space. So it kind of progresses out in circles. Whereas if we look at informed search, we can actually prioritize that search towards the node using that heuristic function. So rather than going out in these circles, we instead can prioritize that search towards the goal. So that's just a little mock-up drawing of what that heuristic function does. So the trick is, in informed search, we use heuristics so that we don't ignore the goal when we select the paths or the next nodes to take off from the frontier. So we have extra knowledge, so let's use it. So the heuristic function is an estimate of the cost of the shortest path from current node n to the goal node, to a goal node. So they can actually be multiple goal nodes. That's why we say a goal node. One catch is it should be efficient to compute, because the whole point is we're trying to make some savings. If it takes absolutely forever to compute, so you get a really, really accurate estimate, you may not actually be making a search any faster. So h of n, we say it does not overestimate if there is no path from n to the goal with a cost less than h of n. So that's just confusing language. Just use your intuition, so it doesn't overestimate the actual cost. Then we define something called an admissible heuristic if the heuristic never overestimates the actual cost. So that means it's always optimistic. So that means it'll always be either the true cost or less. So it does not overestimate. So as an example, if we were let's say at building 42, which is only actually 60 away, or well, actually it's 50, so 10 plus 40 is 50. If it thought it was 70, so if the heuristic function was 70, that would be an overestimate. Now, how could you get a heuristic for this environment? So let's say we're in a map environment. How could you get a heuristic estimate? So you could, for example, instead of looking at these lines, you could look at the bird's eye view. So in a map, rather than actually following the paths that you can take, you could just assume, take a more relaxed problem and simplify it so that you could take straight line distances. And that's one way you could actually estimate distances. So that what I just explained is an example where if we were on a Euclidean plane, that means we're, for example, the map, that cost could be the straight line distance. So hopefully that's intuitive that if you have a map, you could estimate what those shortest paths were by looking at that straight line. If the nodes were locations and the cost was time, you could use the distance to a goal divided by the maximum speed, and that would be an underestimate, so therefore it would be admissible. If it's complicated, you can approximate the solution. So usually, as I explained, a heuristic function can be found by simplifying the problem. For example, you can ignore all obstacles. As we saw with that maze, we could ignore, if I had lots of blocks that you couldn't traverse, you're basically ignoring those. That's what I mean by a simpler, less constrained problem. Okay, so GBFS, the function that uses for prioritization is just h of n, so it's just the estimate. So if we had a priority queue, so remember that in all of these methods, we now make the frontier not just the node, but we also have a cost associated with it. So if we look at my example here, so in this frontier, we don't just store the node, but we also store the cost function f of n. So we have some nodes with priority, so this frontier becomes what's called a priority queue. So you can see that the paths or nodes also have some cost associated with them. So then we select the node, P1, which has the lowest cost. So let's say the lowest cost was C1, and we keep selecting them based off whatever's the lowest cost. And that cost in GBFS, or greedy best first search, is determined by h of n. So now let's look at the properties of GBFS. Will greedy best first search find a solution? So no, it's not guaranteed to find a solution because it depends on the heuristic. Will it generate an optimal solution? In that 2D maze, it was lucky, and the answer was it did find a lowest solution, but is it guaranteed to? Is greedy best first search guaranteed to find the lowest cost path? No. And the complexity, this will depend highly on the heuristic. So we have a worst case of OB to the m, where b is the branching factor and m is the maximum depth of the tree. So this is very similar to depth first search, so it can be exponentially bad. Okay, so we had this example. It's basically the same as what's demonstrated here, but instead of our priority function being the actual path cost traversed so far, it would just be h of n. So now A-star search, it uses both the path cost and the heuristic values. So what we can see with greedy best first search is, yes, if we have a good heuristic, it's going to be very efficient. However, it's not guaranteed to give us an optimal solution. So that's the problem. So one way we can overcome that is by combining the priority function with the actual path traversed with the heuristic function. So that's basically showing this as paths. So you have some starting state to a state n and a goal state there. So you have the path traversed so far, which is g, and the estimate from where you're up to the goal, and that is called f. And so you use that plus an estimate to get your priority function. So it's a mix of the two algorithms, we're up to the the goal, and that is called f. And so you use that plus an estimate to get your priority function. So it's a mix of the two algorithms, so therefore it's algorithmically similar to both, and it treats the frontier, again, as a priority queue, ordered by that priority function f. So that is g plus h, and as a priority queue. Ordered by that priority function f. So that is g plus h. Do people want to see an example worked out by hand? Yes, okay. Right. So let's do a star search. I'll get up the problem. Minimize this for infinite to write out, but some we have explicitly. So we'll have, so it starts off with UQ Lakes. This one you have memorized, so it's easy. And you put it onto the frontier. So the frontier is a, what is its f of n? So its f of n will be the cost so far, and please correct, and we put it and we also put it into the reach. And what do we do? So while it's on goal state, no, and building 78. Now let's do the expansion of the frontier path cost of the heuristic value, which is 100. And please correct me with any maths I do. So last week and the week before I made some errors and people picked up on it, so that was excellent. Please do that again today. Okay, and we put it, and we also put it into the reached or the visited. So we can put that here. So that is state UQ Lakes and has a path cost of 0. And what do we do? So while there's something in the frontier, we take off a node from the frontier with the lowest cost. That is UQ Lakes. Let's take it off. Is it a goal state? No. Now let's do the expansion. So we run expansion on that node. So we get out, what do we get? A, B, and building 78. Those children. So therefore we add it. So we can see that. So we add it so far. What is the cost so far? 50 and the frontier. I'm just doing them two at once just because it's easier that way. G of n is 50 plus h of n is, it would help if you guys read these out so I don't have to like jump through. The 50 plus 53 equals 103. Then for building 78, it is 70 plus 50 equals 120. Okay, now what do we do? We're still in this wild frontier. Are there still nodes in our frontier? Yes. So let's pop it off. What does pop mean? Pop means take off the node with the lowest cost in the priority queue, and the current lowest is 103. So let's pop that. What happens when we pop it? We check if it's a goal state. No, it's not. And now we expand it out. So AB will have 1, 2, 3 children. So building 51, building 50, and building 78. And so what we do is we go through each of those children. Turns out here, when it expands it, it creates a node representation that has state, parent, action, and path cost. So we take out and we figure out what the state was. And now let's check if it's in the reached state already. So building 51 is not yet, so we add it. We add building 50 as well. Now building 78, is it in the reached or visited set? Yes. So it already is here with a cost of 70. What cost do we have? It already is. Now building 78, and now let's check if it's in the reached state already. So building 51 is not yet, so we add it. We add building 50 as well. Now building 78, is it in the reached or visited set? Yes. So it already is here with a cost of 70. What cost do we have? Yeah, I heard some people say 60. So we have a cost of 60. So what we do is this overrides the old one. So if child.path cost is less than reached s.path cost, which it is, we then override it. So this now becomes 60. What do the other ones become? 65, 65, so 50 plus 15, and we add them to the frontier. Turns out we do this one by one, it's just easier to do it this way. So building 51 with a cost of 65 plus something, building 50 with a cost of 65 plus something, and building 78 with a cost of 60 plus 50 equals 110. What are these ones? Building 51 has a heuristic of 30. That's 105. Building 50 has a cost of 38. What's 65 plus 38? Is it 103? Yes, is this all correct so far? Okay, so now what do? We've just added all of those children. Now we have to go back up to here. So sorted by here, yes. 65 plus 38. Is it 103? Yes, is this all correct so far? Okay, so now what do? We've just added all of those children. Now we have to go back up to here. So sorted by here, yes.